Welcome back to the Python programming tutorial series for climate mathematics, theory, and applications. In this video, we will cover Chapter 3, Basic Statistical Methods, Part 3. In this section, we will cover various probability distributions such as the Gaussian and t-distribution. Let's begin with displaying the different cloudiness climates of 3 cities. We will be looking at cities Las Vegas, San Diego, and Seattle, as seen in the labels array. Next, we will set up an array made up of clear probabilities. This clear array will be outlining the probabilities at which it is clear sky in these cities. The cloudy array will outline the probabilities of it being cloudy in those cities. Next, we're going to create the label locations. We're going to be accessing the NumPy package using the arrange method with the length of our labels as our parameter. This will set up an x variable that is evenly spaced so we can attach our labels to the correct locations. We're going to set the width of our bars as seen in the highlighted text. Then we go into preparing our figure. We are going to set fig and x equal to our PLT subplots. So this highlighted line is basically just setting up and preparing our figure for data entry. Next, we will be adding our data to the figure. We are going to be using 2 different types of rectangles, one to display the clear values and another rectangle to display the cloudy values. So our Rex1 now has our data in it that it is going to be displaying our clear sky probabilities. Rex2, in a very similar fashion, is going to display our cloudy day probabilities. We're going to add some labels. We're going to set our Y label, set our title. We're going to set X ticks. So this allows us to see uniformly X tick marks. And then we are going to set our X tick labels. So after we get those appropriately sized ticks on our X axis, we can label them appropriately. We are going to set up a legend also for more clarity. This legend will go based off of the label parameters. So you will be able to see clear and cloudy labels in our legend. Right here, we have created a function to label each rectangle with its respective frequency. We are going to set up the definition of our function, naming it auto-label, with a parameter named rex. Following the definition of the function, we have a short description of what our function does. If you want to learn more about this function, you can look at the documentation for the matplot library method annotate, and it will outline these parameters that are used within this function in order to auto-label our rectangles. Now we are just going to use our auto-label function that we just created on Rex1 and Rex2. This will give us individual labels on each rectangle. Not forgetting to wrap your block of code with a PLT show. This block of code does produce this plot. We can see that we have Las Vegas, San Diego, and Seattle centered on our x-axis. We can also see that we have a legend in our top left corner dictating what rectangles are clear sky and what rectangles are cloudy sky representatives. We can see that our function did actually work with the displaying the heights on the top center of each rectangle. Just a reminder that this plot does show the probability of having clear or cloudy skies in each of these cities. Next, we will be going into a PDF of a standard normal distribution. We are going to be looking at a sample from a normal distribution using the NumPy random generator. We go into the NumPy package. Within the NumPy package, there is a random module, and inside this random module, we are going to access the normal function. We give it a sample size of 100,000, and we name these samples. Next, we are going to compute a histogram of the sample. I'm going to set up some bins. This is going to be an evenly spaced sequence of numbers between -5 and 5, and there are going to be 300 elements in this sequence. Next, we're going to get our data into our histogram. We're going to set histograms and bins equal to our NumPy histogram method. We're going to plug in our samples, let bins equal our variable bins, and we're also going to be setting density equal to true so we can look at our probabilities. We're going to set our bin centers with this function, and we are also going to be computing the PDF on the bin centers from our SkyPy distribution object. So we do get into the SkyPy module. Within that, we're going to access the stats package. We are going to access the normal module inside the stats package, and we are going to be looking at the PDF of our bin centers. We're going to name this variable PDF for easier access. Next, we're going to set up our figure with our fig size. We're going to set our title, set our X label, set our Y label. We are also going to put a grid on our plot. Lastly, we are going to plot using that matplot library plot function on our bin centers and our PDF. So this allows our bin centers to be our X variable, and then we are going to use our Y value as our PDF. We are going to put some text on this plot indicating how much area is under the curve, and then we will wrap our block with PLT show. Once we run this whole block of code, we do get this PDF of the standard normal distribution to pop up. We do have a area equals 1 text right in the middle. I could make it larger if I wanted to put in a font size parameter into my PLT text method. We can make these font sizes bigger or bold. This curve does depict our standard normal curve with a mean of 0 and a standard deviation of 1. We can see right at our mean of 0, we do have the highest probability. Next, we will be looking at some various normal distributions. We're going to be setting up 5 different normal distributions and plotting them on the same plot in order to compare them. So we're going to go ahead and create those 5 different normal distributions. We are going to use bins to create an evenly spaced sequence. This time we're going to be working between -8 and 8, and we do have 200 points scattered in between. We're going to set mu and sigma equal to 0 and 1 respectively. Then these y variables are going to be equaling our normal distribution PDF with mu and sigma inputted into them. So we do get our y1 value from using mu, 0, and sigma 1. Our y2 value is going to be set up in the same fashion, but we are going to change our sigma into a 2. We're still working with mu equals 0 for y2. For y3, we're going to use mu equals 0 and sigma equals a half. For y4, we are going to use mu equals 3 and sigma equals 1. For y5, we are going to use mu equals -4 and sigma equals 1. Next, I'm going to set up a pandas data frame of all of the data that we just created. Our newly defined data frame named df is going to have our first column as our x variable, namely bins, followed by our y1, y2, y3, y4, and y5. This allows us to attach our x variable to any other of the column variables that we are setting up in our data frame. We're going to set up our figure with our PLT figure, setting our plot size. And now comes to the data input area. We are just going to call our x and y variables from their label that they are labeled in the data frame. For our first line, we are going to be using x and y1, specifying our data is coming from our data frame. This one is not going to have a marker, but we are going to use face color red. We do set our label using LaTeX, so we have nicely formatted legends when we use our legend function. We repeat this process 4 more times for the data that is gathered in y2, y3, y4, and y5. Notice we do change the color between each of these lines in order to see the differences between these normal distributions. We do make the labels appropriate for each type of distribution. We do want our legend on there since we do have 5 lines. So we're going to use that matplotlib legend function, and it will plot our legend in an appropriate space. We're going to set our title, set our X label, set our Y label, and once we run this block of code, we do get this normal distribution with 5 different normal curves on it. We can see our red curve labeled on our legend is our standard normal curve. Then we have a blue curve, which is going to have a mean of 0, but a standard deviation of 2. So we do get a wider spread on our blue curve. For our black curve, we have a mean of 0 and a standard deviation of a half. So our spread of our distribution does get tighter for our black curve. Next, our purple curve has a mean of 3, so its highest probability should be right at 3 with a standard deviation of 1. Also, our green curve has a mean of -4 and a standard deviation of 1. We just want to quickly verify our normal equation that we were using to get our y values for that curve. We're going to let mu equals 0, sigma equals 1. We're going to make this int g function with one input parameter x. We are going to return the standard normal PDF. We are going to return the normal PDF with whatever input your x variable is. We are going to use this int g function in a quad function. We're going to let I equal quad. We are going to be integrating from -2 to 2. Then wrapping it in a print statement so we can see our results. We do get the integral evaluated to 0.9545, and we do have an absolute error that is 1.84 e to the -11th. So our int function is actually quite well at depicting the area under these curves. Next, we are going to be going to a student t-distribution. We are going to want to set up that uniformly created sequence. We are going to be creating this sequence between -4 and 4, and it's going to have 200 points within those values. Just a note that the t function in Python does not allow using infinity as a parameter, so we are going to use 100 million to simulate the t distribution with infinity degrees of freedom. So we are going to let our pseudo-infinity be my_inf equal 100 million. We're going to set up our figure with our desired figure size. Then we are going to just go straight into our plotting functions. We're going to plot x with the t distribution, which is dictated just by the t, with 3 degrees of freedom. And we are going to be looking at the PDF of x on the t distribution with 3 degrees of freedom. So this part of the code sets up the t distribution with 3 degrees of freedom, but once we attach our PDF method to it, it is accessing the PDF for your x values on the set distribution. We're going to let this line be red, and it is going to have a label of df equals 3, so we know how many degrees of freedom each line has. Our next line is going to come from a t distribution with 1 degree of freedom. Its color is going to be blue. Then our third line is going to come from a t distribution with 2 degrees of freedom, and its color is going to be black. Then we are going to have a t distribution with 6 degrees of freedom. Its color is going to be purple. Lastly, our final line is going to be a t distribution with degrees of freedom dictated by variable my_inf. This line will be dictated with the color green, and the label df equals inf. We definitely want a legend for this plot because we have 5 different lines. So we're going to use that PLT legend function. Lastly, we are going to label our plot appropriately and wrap our whole block of code with the show in order to produce our student T distribution as seen on the screen. This concludes part 3 of chapter 3, Basic Statistical Methods. In the next video, we will wrap up chapter 3 with a section detailing parameter estimates and their corresponding error.